Hello everyone, I'm Sunbin. Next, I'm going to share our recent work, Neural Network, Semantic Backdoor Detection and Mitigation, a causality-based approach. This is the agenda of my presentation. I will start with introduction and motivation, followed by our problem definition and approach. Then I will share our experimental results, and lastly, I will end with conclusion. In recent years, neural networks are gradually adopted in a wide range of applications, such as fraud detection, facial recognition, self-driving, medical diagnosis, and many others. Hence, neural networks' dependability and reliability is crucial to us. However, neural networks may misbehave in different ways, and backdoor is one of the most challenging defects that can be embedded into a neural network. For example, in these figures, a carefully fabricated eyeglass frame misleads the neural network to believe the face of a white male belongs to the famous actress. And in this work, we focus on semantic backdoor detection and mitigation. As shown by many existing works, backdoors can be easily embedded into a neural network and cause unexpected behavior. And the semantic backdoors is one type of neural network backdoors. It works by manipulating the semantic of an input. One example illustrated here is that the attacker chooses to label all the green cards in the training set to a frog. And after training the model during test time, most of the green cards will be misclassified as frog. Since during the attack or during the testing time, the attacker does not need to actually modify the training sample or the testing sample, the semantic backdoors are more stealthy and it's easier to bypass existing defense methods. And in this work, we are going to solve the problem of neural network semantic backdoor defense. For a given neural network N, the semantic backdoor detection problem is to evaluate whether the neural network contains a semantic backdoor. If it is, we are going to solve the mitigation problem, where it is to construct a neural network N prime such that it's free of semantic backdoor and its accuracy is minimally affected. And in this work, we focus on double targeted attack, where samples from the victim class V carrying the semantic trigger will be classified into the target class T. This slide shows the overall framework of our approach. We call it SODA. It's from semantic backdoor detection and mitigation. And the first stage is that for a given model, we are going to apply causality analysis on it with a known small set of clean samples. And based on the causality analysis results, we are going to be able to identify the backdoor victim and the target class. And at the same time, we will be able to locate a set of responsible neurons that is most suspicious and it contributes most to the attack target class. And in the second stage, we first reconstruct a small set of infected samples based on the identified victim and the target class. And after that, we are going to optimize the weight parameters of the identified responsible neurons in order to remove the backdoor. And in this process, we are going to make use of a set of clean training samples and the reverse engineer the infected samples. And lastly, the repaired model will be returned as the result. And next, we are going to present details of each step in our approach. Firstly, how to detect semantic backdoor. Semantic backdoor exists because certain neurons capturing certain semantic features contribute to the wrong prediction. For this example, the neurons capturing green and also wheels driving contribute to the class frog instead of cars. Hence, by understanding how neurons contribute to the prediction classes, we can potentially find problematic patterns for identifying semantic backdoors. Firstly, how can we conduct causality analysis on a given neural network in order to detect and mitigate such a backdoor? And this slide shows how we are going to calculate the causal attributions of a hidden neuron X to the class activation YC. Based on these two equations, we make use of causal intervention on the neuron X and a small set of clean samples. And by calculating the CA, we will be able to measure the effect of neuron X being activated on class YC. And next, how can we detect the target class T? And here, for samples from each source class, we are going to calculate the CA of all neurons in a selected layer for all the prediction classes. And in this example, we show 4 classes, 0, 1, 2, and 3. And after that, we make use of Pearson correlation coefficient, which is used to measure the similarity of 2 CA distributions. And here, for each source class, we calculate the PCC between the CA of each prediction class and the average CA of all the rest of the remaining prediction classes. And we repeat the same for all the source classes, and then we will have the results as illustrated in the second table. And in the last, we calculate the average PCC of all the prediction classes. And intuitively, abnormal small PCC here reveals unusual CA, which is a sign of semantic backdoor. And hence, in this step, the prediction class with abnormal small PCC is identified by SODA as the target class. And nextly, how do we detect the victim class V? And in this step, for the samples from each source class, we analyze the prediction value of YT. We calculate YT for samples from all the source classes. And here, abnormally large YT will reveal the victim class because some benign features from the victim class will also contribute to the target class wrongly. And next, how can we remove the backdoor from the given model? And in this step, we first reverse engineer a set of infected samples based on the identified victim and target class. We optimizing the clean samples from the victim class towards the target class. And after that, together with a known small set of clean sample, we optimize the weight parameters of the responsible neurons identified previously. And here we make use of SGED optimization, and also the loss function is used as shown here. The first term is to make sure that both infected samples and also the clean samples are classified into the right class. And the second term further penalize the infected samples to be classified into the target class. And after a few epochs, we will have the repaired model returned as the result. SODA is evaluated over 21 neural networks trained on 6 benchmark datasets. And for each dataset, we conduct 2 kinds of semantic backdoors, and also we train 1 clean sample for comparison. And the figures here shows the example infected samples for some of the models like wing cars, or turn left side in dark background, also plate shirts. And next, we are going to evaluate the detection performance of SODA. This table summarizes the result. The second column shows the actual backdoor embedded into each model, and the third column shows the backdoor detected by SODA. As we can see from this result, SODA is able to detect all semantic backdoors correctly. Next, we are going to evaluate the mitigation performance. And here we apply SODA on all the affected models or attacked models. And also here we report the change in attack success rate before and after applying SODA, and also change in model accuracy. As we can see from this table, on average, after applying SODA, the attack success rate dropped from greater than 80% down to 0%, and also the model accuracy is minimally affected, where on average it reduced by around 2% only. Lastly, in conclusion, in this work, we propose and implement SODA to detect and mitigate semantic backdoors. It first conducts causality analysis to identify attack target classes and response neurons. Then it optimizes responsible neurons to remove the semantic backdoors. We empirically evaluated SODA on 21 neural networks trained on benchmark datasets, and the results indicate that SODA is able to effectively detect and mitigate semantic backdoors, and it outperforms existing state-of-the-art approaches. Thank you, everyone. This is the end of my presentation.